Hello there, it's me, Thomas again. Today I'm here in Rotterdam, the biggest seaport in Europe, to talk about density and buoyancy and to see how this huge ship, which is made of steel and weighs thousands of tons, is able to keep afloat in water. First, we'll see a little story about Archimedes, a great man of the antiquity and had an idea that is still used today. Then we'll have a little explanation on things like density, mass, and volume. And at the end, we've got two experiments to work at home. I hope you like it. Let's start.
Long, long, long time ago, in the old Greek city of Syracusa, there was a king called Hieron, and there lived a man called Archimedes, who was very famous as a genius. Archimedes was a mathematician, a scientist, and an inventor. One day, the king wanted a new crown. So he gave the goldsmith some gold coins to make them into a gold crown. But when the goldsmith brought back the crown, the king was suspicious that he had stolen some coins and mixed some silver on it. So the king asked Archimedes to discover if the goldsmith was lying. So Archimedes thought long and long and long about the problem, till one day, while he was sitting in the bathtub, he had an idea that could solve the problem. So he jumped out of the bath and ran naked on the streets of Siracusa, shouting, "Eureka! Eureka!" which is Greek for "I found it! I found it!" Archimedes realized that to know if a crown was really made of gold, he had to know its density. Density is of course mass divided by volume, and density of gold is different to that of silver. So if the crown was made of a mixture of gold and silver, he would know by knowing its density. But to do so, he had to know the volume of the crown. And that was very difficult because the crown wasn't a regular figure like a cube or a square where you can measure and multiply to get the volume. What he could do is dip the crown into water and measure the volume of water displaced by it, and use that volume to figure out the density of the crown and compare it to that of gold and silver. Archimedes took the crown and the same weight of gold coins and put them into water. As the crown displaced more water, he knew that the goldsmith was lying, and it was the end of it for him. This way of measuring volume by dipping things into water is called Archimedes' principle. You can think of it next time you're in the bathtub, and maybe you can come up with some brilliant idea. Eureka! So, we learned from the video that Archimedes' principle says that if you dip an object into a liquid, the volume of the object displaces exactly the same volume of the liquid. You can see it here. When I dip this little wave in water, it displaces some volume of water that overflows and falls into this beaker, and is the same volume. This volume of water is the same as the volume of the object I have dipped into water. And the object experiments a force upwards, which is equivalent to the wave of the water or of the liquid that has been displaced. So here you see that this wave reads 5 kilograms on these scales, and when I dip it into water, it only reads 3 kilograms, because the other 2 kilograms is exactly the weight of the water that has been displaced. You can experiment that when you are in the swimming pool or on the beach, in the sea, and you see that you feel you weigh less when you're in water. So here there's a little simulation to put Archimedes' principle to the test. You can find the link in the description of the video. Here you've got some controls. Here is a block of different materials with different weight. This one weighs 2 kilograms. And here is a tank of water that has 100 liters of volume in it. So I'm gonna change first to something more dense, like for instance brick. Okay, this cube made of brick is 10 kilograms in mass. So if I dip brick into water, what do you think it will happen? Of course, it sinks, doesn't float. You see now that water is displaced exactly 5 liters. So the volume of this object is exactly 5 liters, and the weight of the object is 10 kilograms. So the density of brick, this substance, the density of brick is about 2, isn't it? 10 kilograms divided by 5 liters gives a density of 2 kilograms per liter. The mean density of water is 1. So as this one is more dense, it doesn't float, right? What happens if I change it for ice? Okay, ice. So ice is the volume is all the same. It's 5 liters again, but the weight now it's 4.6 kilograms. So it gives a density of 0.92 kilograms per liter. Now I ask you, will it float in water or will it sink? What do you think it will happen? Well, for those of you who doesn't know, actually ice floats on water, okay? Because its density, 0.92, is less than that of water, which is 1, okay? The density of water is 1, so anything over 1 kilogram per liter will sink, and anything which is less dense than water will float. Okay, so ice floats into water. And what if I change it for wood? Is only 0.4 kilograms per liter, is 0.4 kilograms per liter. So it means that it has a volume of 5 liters but a weight of only 2 kilograms. So if I dipped it into the tank, it floats. We can learn something more about this experiment. See that some part of the wood block is over water and some of it is under the water. Can you tell me why is it that some of the block is under the water, and it doesn't matter if I push it downwards, it goes up and stays at the same position? Okay, see that the part that is under the water is exactly 2 liters in volume. So from the 5 liters of the block, only 2 are underwater. And why is it so? Well, precisely because the water displaced by this wood, these 2 liters of water, weigh exactly 2 kilograms. As water density is 1 kilogram per liter, if I have 2 liters of water being displaced, then I have 2 kilograms of water, and they push the block upwards, so they compensate for the 2 kilograms of wood. Okay, that's why it keeps afloat and it doesn't sink. If I change this for styrofoam, which is this sort of plastic you can find in food packaging. This is very light. It's only 0.75 kilograms, but the volume is all the same. It's 5 liters. So if I dipped it into water, flips, it floats. Oh, it readily floats. Very good. And the volume of the liquid displaced, that is to say the volume of this object which is underwater, it's only 0.75 liters, because that is the weight of water that needs to be displaced for this object to float. Okay, here you've got different options, different controls, so you can change and have the same mass with different volumes and test whether they float or they sink. You see that these three objects are same weight, 5 kilograms, but since they are more dense than water, they sink. However, this one, as it has a bigger volume, it floats. This one simply has 10 liters of volume, and only 5 of those liters go underwater to support the rest of the block. If I have objects with the same volume but different weights, I can test whether these objects are able to float or not, and I see that these two objects, as they are only 2 or 4 kilograms of weight and they are all 5 liters of volume, these two won't float, but these two will float. This one has 4 kilograms in 5 liters is a little less than 1. Okay, 4 divided by 5 is less than 1, so they float. You need to remember that density in water is always 1, so anything that is less dense than water floats. Alright, you can have different objects with the same density. Okay, so you've got this object, for instance, is exactly 2.5 liters of volume and only 2 kilograms of weight, so the density is less than 1 and it floats. This will float, this will float, this one floats, and that one floats as well. All of them float. You can have a go and put this Archimedes principle to the test. You will find the link to this simulation on the description of the video. Now, let's have some kitchen experiments. First one is really easy. All you need to do is to find some substances that are different in density and arrange them in an order so that the most dense is at the bottom and the less dense is at the top. So you color them with food coloring and have an arrangement of colors, which is very lively. So let's get down to it, okay? For this experiment, all you need is to find some liquids at home that have different densities. I give you some ideas, but you can find different liquids at home, maybe different to these ones. Cleaning alcohol, vegetable oil, water, dishwasher liquid, and you will also need some salt, some food coloring, different colors, and glasses to keep the liquids in it. And you will also need some scales to weigh. Okay, now get one empty glass and make a mark like that green mark you see there and put it on the scales. Now you read on the scales that that glass is 79 grams, so the weight of the glass is 79 grams. Now write it down on a piece of paper. You write empty glass, 79 grams. Now have some water and pour it into the glass slowly and carefully till you reach the mark. So be as precise as you can. Alright? Once you've done that, you read on the scales 154 grams and you write it down. Water 154 grams. Do the same with the vegetable oil. This one is sunflower seed oil. Fill the glass to the mark and I read 147 grams. Write it down. Vegetable oil, 147 grams. I do the same with dishwasher liquid. To the same mark, the same amount of dishwasher liquid weighs 156 grams. Write it down on the paper. Dishwasher liquids, 156. And now is the turn for alcohol. You see that cleaning alcohol is a little lighter. It weighs 146 grams all together with a glass. So I write it down and pour the alcohol in a different glass. Now, once you've done that, you get an empty glass and pour water to the same amount as you did in the first place. You can use the readings on the scales to be precise. You can read 154 grams of water and then put some salt in it. It doesn't really matter how much salt you put in it. Here you see you can read 162. A couple of teaspoons will do. Once you've done that, stir the mixture so the salt dissolves. Then you have a different density for that liquid. It's going to be more dense than plain water. Now you can label the different liquids with some tags to make sure you don't mix them, and you use food coloring. As you can see, since dishwasher liquid is already green, I'm not going to use any more coloring on it. I'm going to use other 4 colors in the remaining 4 liquids: salty water, plain water, vegetable oil, and alcohol. And this is what you get. You see that vegetable oil doesn't really take that red color, so you might want to try a different food coloring. This one isn't working. And here comes the really tricky part of the experiment. You need to pour the liquids down the sides of the glass to prevent them from mixing from the most dense to the less dense. So I started out with a dishwasher liquid, and then I realized that salty water is even denser than dishwasher liquid, so it came down to the bottom of the glass. Now I'm pouring water, clear water, and as you can see, it floats over the dishwasher liquid. And so I'm using a bottle with a special cap on it. Using this, I can suck some liquid from the glasses and pour it down the walls slowly and carefully to prevent the liquids from mixing. You see the layers forming. Yellow one is salty water, the green one is dishwasher liquid, and blue one is water. And now I'm going to use vegetable oil. You see we didn't have luck with food coloring, and it didn't really taint the liquid. You see I'm pouring now vegetable oil and it's sitting on top of water. See? It's really easy. Now you have to do that carefully so they don't go down and mix. Now this one is a yellow layer of vegetable oil, and this is the result. You can see there the different layers, the 5 layers. The one at the bottom is salty water, then is dishwasher soap, then it's plain water, vegetable oil, and alcohol on top of that.
How did it go? Did you manage to set up the different layers? Sometimes it takes some practice. Now it's time for our second experiment. This one is called the submarine. It's quite fun. Let's do it.
To do this experiment, all you need is paper clips, drinking straws, scissors, and a bottle of water. First, you cut a piece of a straw which is double the length of the paper clips, as you see in the picture. Now you fold a piece of straw in half and hold it with the paper clip, like that. Just make sure it is hold tightly like this with the paper clip so it forms a sort of a loop. Fill up a plastic bottle with water to the rim, to the very top, and put your paperclip and straw in it. Check that it floats, and then put the lid on and close it tight. Then press the bottle hard. You might need the help of an adult. And this is what happens. If you press it hard, your submarine will go down, will dive, and if you ease the pressure, it will go up again. You need to press it really hard, so you might want to ask an adult for help. You can use different sizes and shapes. Here you've got a different bottle and the result is all the same. Press it and it will go down. So, how did it go? Did you manage to go up and down with the submarine? Now remember the links to the resources and a place to post your pictures. See you around!